tensile force, bending moment, or torsional moment, or combination of these. Okay, so you have to design shaft on strain basis. You need to consider all these things. Okay, whether it is axial tensile force, whether it is bending moment, or whether it is torsional moment, or there may be the combination of bending moment or torsional moment on that particular transmission shaft. Okay, so the design of a transmission shaft, which consists of determining the correct shaft diameter from strength and rigidity consideration. So very most important point in a shaft design is to find out or to determine the correct shaft diameter. Otherwise, what will happen if you not properly find out the correct shaft diameter, then if sudden impact or sudden force will come onto that shaft, it may get failed. Okay, so on the basis of strength and rigidity consideration, your task is, or the designer task is, to find out the correct shaft diameter of that particular shaft, of that transmission shaft. Okay, so you need to consider the strength and rigidity while designing the shaft. Okay, so when the shaft is subjected to the axial tensile force, okay, when your shaft is subjected to the pure axial tensile force application, then the tensile stress is given by the formula that sigma t, that is force upon area. Okay, the force which is coming onto that particular shaft upon cross sectional area of that shaft. Okay, so sigma t, that is tensile stress, is equal to P upon pi by 4 into d square, where t is the diameter of the shaft. Now that shaft is in solid. Okay, that consideration of the shaft is a solid one. Okay, so tensile stress is equal to P upon pi by 4 into d square. Okay, when your shaft is subjected to the under pure tensile force application. Okay, so here is the you can find out the tensile stress due to that axial tensile force, which is of P upon pi by 4 into d square. Okay, so sigma t is equal to, just rearranging the term, that denominator 4 will go to the numerator. So sigma t is equal to 4p upon pi into d square. So by using this formula, you can find out the tensile stress in that particular shaft. Okay, okay, so now the next point, when the shaft is subjected to the pure bending moment only. Okay, now earlier case was axial tensile force application only. Now but when the shaft is subjected to the pure bending moment, and then the bending stress is given by the formula sigma b is equal to mb into y divided by I, where mb is nothing but bending moment into y, that is perpendicular distance from the neutral axis, and I is the moment of inertia about the axis. Okay, so bending moment into y upon I, where you can find out the bending stress. Okay, so which is equal to mb into y is nothing but d by 2. Okay, the perpendicular distance from the neutral axis, and divided by moment of inertia for the circular solid shaft is pi by 64 into d raised to 4. Okay, so by rearranging the term, what will you get? Sigma b is equal to 32 mb, that is 32 into bending moment upon pi d cube. This will be the modified equation once you will modify this one. Okay, so bending stress, by using this formula, you can find out the bending stress in that particular shaft, which is of 32 mb divided by pi d cube. Okay, now the next thing, when the shaft is subjected to a pure torsional movement only. Okay, now earlier case was your shaft was subjected to the pure bending movement. Okay, that's why bending stress is, finding out the bending stress is important. But when your shaft is subjected to the pure torsional movement, then you need to find out the torsional shear stress in that case. Okay, now how to find out that torsional shear stress? Okay, when your shaft is subjected to the pure torsional moment, now formula that tau is equal to mt into r divided by j, where m suffix t is nothing but the torsional moment. Why? Because your shaft is under torsional moment. That's why you need to consider torsional moment into r divided by j, where j is the polar moment of inertia. Okay, here in that case it is a moment of inertia. Okay, but here is polar moment of inertia. Okay, so mt, now r is d by 2, where polar moment of inertia for the solid circular shaft is pi by 32 into d raised to 4. Okay, but here moment of inertia is pi by 64 d raised to 4. Okay, So J is polar moment of inertia is pi by 32 into d raised to 4. So where if you rearrange all the terms, the tau, that is torsional shear stress, is equal to 16 into mt, that is torsional moment, divided by pi d. Okay, if you compare these two formulas, sigma b is equal to 32 mb by pi d cube and tau is equal to 16 mt by pi d cube. There is only term difference is that here is 32 mb and here is 16 mt. Here is torsional moment, here is bending moment. The denominator is same, that is pi d cube. Okay, so just you have to remember this formula to find out bending stress and to find out the torsional shear stress. Okay, this is 32 mb by pi d cube, 16 mt by pi d cube. Okay, you have to use this formula if you want to design your shaft on the basis of strength. Okay, on the basis of strength criteria, you can use these three formulas. Okay, tensile stress, bending stress, and torsional shear stress. So by using these three formulas, you can find out these three parameters. Okay, all of you, are you getting this? Should we go ahead? So this is about tensile stress, bending stress, and torsional shear stress. Okay, okay, is it fine up till this? Yes, please. Yes, are you here? Are you listening me? Is it fine up till this? Yes. Okay. Okay. Should we go ahead? Yes, we will go ahead now. Now this is the shaft design on strain basis. Okay. Okay. Now the next point. Yes. Now the shaft can be designed on the basis of maximum principal stress theory or maximum shear stress theory. Okay. Maximum principal stress theory or maximum principal shear stress theory. Okay, principal stress theory and principal shear stress theory. Okay, on that basis also we can design a shaft. Okay, now how to design, what formula we have to use? Now first is we will see about maximum principal stress theory. Now what is maximum principal stress theory? In that maximum principal stress, it is denoted as a sigma 1. The maximum principal stress is denoted as sigma 1. Okay, since the shaft is subjected to the bending and torsional moment without any axial force. Okay, so in that case, there is a combination of bending and torsional moment. Earlier, we have seen when your shaft is under pure bending, when your shaft is under torsional moment. So we have seen two formulas in earlier slide. Okay, but when your shaft is subjected to the combined loading, when it is under bending as well as it is under torsional moment, okay, but without any axial force. Now in that case, how to find out the dimensions for that particular shaft, okay, or how to find out the stresses which are induced in that shaft when your shaft is subjected to the both, that is combination of bending and torsional moment. Okay, so here now formula already we have seen, that is we are also consider here sigma s, that is normal stress or bending stress. Sigma b is equal to 32 mb upon pi d cube. Okay, in earlier slide we have seen this formula, and this formula tau, that is torsional shear stress, tau is equal to 16 mt divided by pi d cube, where mt is torsional moment and mb is bending moment. Okay, in earlier slide we have seen this formula. Okay, that sigma x is nothing but normal stress. Okay, normal stress, it is also equal to bending stress. Okay, and 32 mb upon pi d cube. Okay, where tau is equal to 16 mt upon pi d cube. Okay, now the principal stress sigma 1 is given by, now there is a formula how to find out the sigma 1, that is maximum or principal stress, that is sigma 1 is equal to sigma x by 2 plus square root of sigma x by 2 bracket square plus tau square. Okay, when there is a combination of a principal stress theory and maximum shear stress theory, according to the Mohr circle this formula comes. Okay, so sigma 1 is equal to sigma x by 2 plus square root of sigma x by 2 bracket square plus tau square. Now you can put sigma x from this equation because sigma x is equal to sigma b, that is normal stress. Okay, so I will put all the values here. My sigma x is 32 MB by pi d cube by 2 plus square root. So I will put all the things over here. Tau, I will put that tau, that is a torsional shear stress formula over here. Now what I will get, okay, that we will just see what will be the modification. Okay, now the principal shear stress, that is tau max, is given by, now there is a formula, that is tau max is equal to square root of sigma x by 2 bracket square plus tau square. Okay, if you want to find out the principal stress, you need to use this formula. If you want to find out the principal shear stress, in that case you can use this formula. Okay, so there is a difference is of only this one. In case of a principal stress, there is a sigma x by 2 plus this term, and in case of a principal shear stress, tau max, only this term. Okay, so these two formulas you need to remember. Okay, now sigma x, you know, you can put that sigma x over here and you can modify the equation. Okay, now we will see how it is going to modify. Okay, now that normal stress is denoted by sigma x. Yes, already I have told you that sigma x is nothing but the normal stress. Okay, and the shear stress is denoted by tau. Okay, this is torsional shear stress. Okay, okay, now sigma 1, now I will put sigma 1 here. Now sigma x by 2 means, now okay, 32 MB by pi d cube by 2, that 2, and if I divide 32 by 2 means it is 16, so 16 MB divided by pi d cube plus, okay, here I am modifying this equation, I am putting that sigma x in this equation, so 16 MB divided by pi d cube square plus, now tau is 16 into mt divided by pi d cube square. Okay, all of you, are you getting these equations? Yes, I am putting values in that above equations, and we are going to modify it. Are you getting it? Yes. Once I will modify it. So sigma 1 is equal to 16 upon. Now I will take that 16 upon pi d cube as a common. Okay. So 16 upon pi d cube as a common. So in a bracket, mb is remaining over here. mb plus in square root of mb square plus mt square. Okay. Because I am taking common 16 upon pi d cube, which is outside of that bracket. Okay. So in a bracket, you will get mb plus square root of mb square plus mt square. Okay, so by using that formula, you can find out the principal stress, that is sigma 1. Okay, principal stress you can find out by using this formula. Okay, so now, as you know, sigma 1 is equal to yield strength upon factor of safety. Okay, you can put value here, over here, and you can find out the diameter. Okay, so sigma 1 is nothing but yield strength, okay, in a tension upon factor of safety. Okay, already we have seen that formula. Okay. Okay, now these equations are used to determine the shaft diameter on the basis of principal stress theory. Now, by using this equation, we can find out the shaft diameter. Okay, and I know each which is on the basis of principal stress theory. Okay, so experimental investigation also suggested that the maximum principal stress theory gives the good prediction for brittle material. Now that principal stress theory is used in case of a brittle material only, because experimental investigation shows that it is not applicable to the ductile material. The principal stress theory is applicable, or it gives the good result in case of a brittle material. Okay, and the shafts which are made of ductile material like steel, and therefore this theory is not applicable to the shaft design. Okay, so the shafts which are made of a ductile material like steel, in that case you can't use this principal stress theory. If your shaft is made of brittle material only, that is cast iron like, then you can use this principal stress theory. Okay, means your principal shear stress theory will be applicable in a ductile material. So just remember that thing. This type of a question may be asked. Principles, if the material is of brittle material, which theory has to be used for the shaft design? So in case of a brittle material, principal stress theory. In case of a ductile material, principal shear stress theory. Okay, is it fine? Okay, should we go ahead? Now this is about maximum principal stress theory. Now the next slide will be for the maximum shear stress theory. Okay, or the principal shear stress theory. Maximum principal. Okay, so should we go ahead? Yes. Okay, now the maximum shear stress theory. Okay, earlier it was maximum principal stress theory only. Now here it is maximum shear stress theory. Now the design of a shaft on the basis of maximum shear stress theory. Okay, now the principal shear stress, that is tau max. Okay, now the principal shear stress tau max is nothing but, okay, tau max, which is square root of sigma x by 2 bracket square plus tau square. I think we have seen the formula earlier. How it comes? Tau max here, sigma x by 2 bracket square plus tau square. This is of principal shear stress. So sigma x, you know, 32 mb by 2, that is 16 mb by pi d cube square, plus tau is 16 mt by pi d cube sub bracket square. So same here we have done. So 16 mb by pi d cube bracket square plus 16 mt by pi d cube bracket square. So now which will be the term is common? 16 upon pi d cube is the common term, and which is of a square, so square and square root will get cancelled. So 16 upon pi d cube will come outside, and the part which is under square root is of mb square plus mt square. Are you getting these equations? Yes. So tau max is equal to 16 upon pi d cube into square root of mb square plus mt square. Okay. So according to the maximum shear stress theory, that is shear strength in a that is yield strength in a shear is equal to 0.5 times of a yield strength in a tension. Okay, that relation you already know. So the permissible value of a maximum shear stress theory is given by tau max is equal to yield strength in a shear divided by factor of safety, which is equal to 0.5 times of a yield strength in a tension divided by factor of safety. So already this relation you already know. That relation you have to use while solving the problem. Okay. So the above equations are used to determine the shaft diameter on the basis of maximum shear stress theory. So this formula, that is tau max, okay, is equal to 16 upon pi d cube in square root of mb square plus mt square. This formula you can use if you want to find out the shaft diameter on the basis of maximum shear stress theory. Okay, so by using this formula you can find out the diameter. Okay, so the maximum shear stress theory is applicable to the ductile material, right? The earlier, the maximum principal stress theory was applicable to only brittle material, but the maximum shear stress theory is applicable to the ductile material. Since the shafts are made of a ductile material, it is more logical to apply this theory to shaft design rather than designing the shaft on the basis of principal stress theory. So generally, for the ductile material, we are using the maximum shear stress theory. Okay, and for brittle material, maximum principal stress theory. Okay, that is the difference. Okay, and these are the formulas. Okay, so according to the maximum shear stress theory and maximum principal stress theory. Okay, so tau max. Okay, now the same formula we have written over here. Tau max, that is maximum shear stress, is equal to 16 upon pi d cube in square root of mb square plus mt square, where sigma 1 is nothing but what? Principal stress. Okay, the formula is 16 upon pi d cube in bracket mb plus square root of mb square plus mt square. Only difference in that formula is here in case of a maximum stress theory, only mb is there. That is bending moment plus the remaining term. But in case of a maximum shear stress theory, there is a not bending moment here. Only the change in formula is only this one. Otherwise, remaining is same. 16 upon pi d cube is same, and here is mb plus square root of one, that two things, and here it is same. Okay, so this is the maximum stress theory and this is the maximum shear stress theory. So by using these two formulas you can find out the diameter on the basis of shear stress theory and principal stress theory. Okay, is it fine up till this? Should we go ahead? Yes, you got these formulas, two formulas based on maximum shear stress theory and maximum principal stress theory. Okay, these two formulas you have to remember throughout this unit because you have to use these two formulas to find out the diameters. Okay, is it fine? Yes. Yes, please reply. Yes. Okay, I will go ahead now. Now, the equivalent torsional moment. Now, what is equivalent torsional moment? The expression square root of mb square plus mt square that we have got in earlier slide, that is in case of a maximum shear stress theory, square root of mb square plus mt square. Now that expression is called as a equivalent torsional moment. Now what is equivalent torsional moment? It is defined as when it is acting alone. Okay, when in that particular shaft there is only torsional moment, then it will produce the same torsional shear stress in the shaft as under the combined action of bending moment and torsional moment, right? So equivalent torsional moment is what? When when it is acting alone, that is torsional moment, it will produce the same torsional shear stress in that shaft when it is there is a combined action of a bending moment and torsional moment. Now, what is equivalent bending moment? Now, this expression, that is mb plus square root of mb square plus mt square, that expression is called as the equivalent bending moment, which we are getting in a प्रिन्सिपल स्ट्रेस थेरी. मगाशी आपण प्रिन्सिपल स्ट्रेस थेरीमध्ये आपल्याला हे इक्वेशन मिळालं होतं आणि हे इक्वेशन आपल्याला प्रिन्सिपल और मॅक्सिमम शियर स्ट्रेस थेरीमध्ये मिळालं होतं. So that equation, that expression is called as a equivalent bending moment. Okay. Now the equivalent bending moment is defined as it is the bending moment which when acting alone, okay, when it is which when it is acting alone, and it will produce the same bending stress, okay, same bending stress which may be in tensile or in compressive in the shaft as under the combined action of a bending moment and torsional moment. Okay, so it will produce the bending stress, okay, above equation which will produce the torsional shear stress due to what? The action of a bending moment and torsional moment. Okay, in case of a equivalent bending moment, it will produce a bending stresses due to the combined effect of a bending moment and the torsion moment. Okay, so this is about the equivalent torsion moment and equivalent bending moment. Okay, so, so the concept of equivalent torsional moment is used in the design of a shaft on the basis of maximum shear stress theory of failure. Okay, and when we will use the equivalent bending moment? When it is used in the design of a shaft on the basis of maximum principal stress theory of failure. Okay, so when we'll use the equivalent torsion moment on the, when the design of a shaft on the basis of maximum shear stress theory. When you will use the equivalent bending moment concept when you will design of a shaft on the basis of maximum principal stress theory of failure. So this is the most important criteria when to use equivalent bending moment and when to use the equivalent torsional moment. Okay, are you getting this up till this? Should we go ahead? Because all these formulas are most important while solving the problems. You have to use all these formulas. Okay, so keep in mind or note it down all these formulas while lecture is going on, so that it will be possible to, so that you can get idea about that how the formula comes. Okay, so in ongoing lecture you can note down all the formulas. Okay, now the next, the shaft design, another last point of this lecture, the shaft design on basis of a torsional rigidity. Okay, now on the basis of torsional rigidity, how you are going to design a shaft. Okay, so in some applications, the shafts are designed on the basis of either torsional rigidity or lateral rigidity. Okay, so on the two types of a basis, we can design a shaft. So a transmission shaft is said to be rigid, okay, on the basis of torsional rigidity. If it does not twist too much under the action of external torque, then you can say that that transmission shaft is rigid, and on the basis of torsional rigidity, you can design a shaft. Okay. Now, what is lateral rigidity? Similarly, when the transmission shaft is said to be rigid on the basis of lateral rigidity, when it does not deflect too much under the action of external force or under the action of bending moment. So, in that cases, you can design a shaft on the basis of lateral rigidity. Okay? If it is not twisting too much under the action of external torque, then you have to design the shaft on the basis of torsional rigidity. Okay, And if your shaft is not deflecting too much under the action of external force or bending moment, then you have to design your shaft on the basis of lateral rigidity. Okay. Okay. So in certain applications like machine tool spindle, it is necessary to design the shaft on the basis of torsional rigidity. Okay, that is on the basis of permissible angle of a twist per meter length of the shaft. Okay, and that angle of twist, that is theta r in a radian, is given by theta r is equal to mt into L divided by J into G. Okay, so that is torsional moment into L, that is length, into polar moment of inertia, and modulus of rigidity, G. Okay, so this is equation called as A. Now we will convert that theta r, that is angle of twist, from radian to degree, that is theta r to theta. So we will multiply and divide by 180 and divided by pi, 180 by pi. Okay, while we are converting from radian to degree into mt into L divided by J into G. Okay, so for a solid circular shaft, your J, polar moment of inertia, is pi by 32 into d raised to 4. Okay, now I will put that J in this equation. Okay, so just call it as equation number B. Okay, so combining equation A and B, I will put that J in equation A. So what you will get, theta is equal to 584 into mt into L divided by g d raised to 4. Once I will put that B equation in that A. Okay, so theta r we are converting into theta, okay, in degree. So finally equation you will get 584 into mt into L divided by G into T raised to 4, where theta is what, angle of twist in a degree, where L is what, length of the shaft which is subjected to the twisting moment. What is mt? It is torsional moment. Okay, what is G? It is modulus of rigidity. And what is small d? It is shaft diameter. So all that angle of twist they will provide you, length they will give you, torsional moment value they will give you, the modulus of rigidity value they will provide you, and accordingly, just by, if you know the formula directly, you can find out the shaft diameter. Okay, and that shaft diameter is on the basis of torsional rigidity. Okay, so the above equation is used to design the shaft on the basis of torsional rigidity. Okay, so this is about the design of a shaft on the basis of a strength. Okay, so strength basis we can design a shaft. Okay, that is finding out the diameter of that particular shaft. Okay, is it fine? Now what we have seen today, design of a shaft on the basis of torsional rigidity. Okay, and then these are the equations. Then we have find out what is equivalent bending moment, what is equivalent torsional moment. Then we have seen about the maximum shear stress theory. Okay, designing of a shaft based on the maximum shear stress theory. Then these are the two formulas. Okay, this one is the maximum stress theory and maximum shear stress theory, and then the design of a shaft on the basis of maximum principal stress theory, that is delta 1 is equal to this formula. Okay, and now then first was the design of a shaft on the basis of strain basis, that is if it is of a pure bending moment, if it is of a pure torsional moment, or if it is of an axial tensile force. Okay, so these are the formulas we have seen today. Okay, so this is about maximum principal stress theory, and then the maximum principal shear stress theory. These are the various formulas, and then equivalent torsional moment, equivalent bending moment, and your design of a shaft on the basis of torsional rigidity basis. So all these things we have covered today. So so these formulas, whatever we have seen today, these are the most important one, and you have to use it for the solving the problem based on the design of a shaft. These are the most important formulas you have to use. Okay. So up till this, anybody having any doubt? Are you got this? How it comes? How the formulas comes? Okay. So tomorrow's lecture we will see about design of a shaft based on a ASME code. Okay, that is American standard. Okay, that ASME code generally the design of the shaft will be based on a ASME code. That is the most important one. The directly there will be a problems in the exam for 10 marks which will be based on ASME code. Okay, directly they will give you the problem statement, and they will ask you design the shaft on the basis of ASME code. Okay, on that ASME code the same formulas we are going to use, don't worry. So there is a standard procedure, you have to follow the standard procedure and you have to design the shaft. Okay, that is design of a shaft on the basis of a ASME code. Okay, so in